Welcome to part 3 of lecture 2. So in these last two parts, what I want to do is talk about what things can you deduce from the axioms of a vector space. Okay, so a vector space has many, many properties, but when we defined our vector space, and here let me go back a couple slides here, the vector space was only given 7 properties that it has. Now, amazingly, from the 7 properties, we can start deducing a whole bunch of new facts that are true. And so that's kind of what I want to do here, but also take the time to write out the proofs because this course is focusing on how to write proofs as well as learning the background. So the first theorem here, okay, so let me just kind of make myself disappear so that we have a little bit more space on the screen. The first theorem here is just saying that the additive identity of your vector space is unique. Okay, so the additive identity is the 0 element, and it has the property that no matter what I add to 0, I get back the thing that it starts with. Okay, now to prove this, we're going to say, well, let's suppose that there were 2 different ones, right? So suppose 0 and 0 prime are additive identities of my vector space V. Right? Well, then what could we deduce from them? Well, then we know that 0 has to have the property that if I take 0 and I add it to 0 prime, right? So 0 plus 0 prime is 0 prime's an additive identity, that gives me 0. Okay, but on the other hand, we have that addition commutes. Okay, so here, maybe I'll write out the various pieces, right? So this identity follows from the fact that 0 prime is an additive identity. This equality just follows from the fact that addition commutes. And then this property here follows from the fact that 0 is an additive identity. Okay, so we have 0 is equal to this term, which is equal to this term, which is equal to 0 prime. But now you look at the 2 endpoints and we have that 0 is equal to 0 prime. So you can only have one additive identity. All the additive identities you find actually have to be the same element. And just remember when we reach the end of a proof, we put a little square there, just to remind the reader that we've reached the end of the proof. Okay, so this is a good example of the type of proof that you can do in linear algebra. Okay, now it looks like I didn't leave myself a lot of room here, but let's see if I can squeeze in the proof. So the second result is kind of similar. It's saying that the additive inverse of each v, okay, so remember it's saying at one of the axioms is saying that there is a w such that v plus w is 0. It's saying this theorem is saying that it's unique. Okay, so every element has an additive inverse. I can find something to add to it to get to 0. The theorem is saying that that w you can find is unique. Okay, and the proof is kind of looks very similar. So let's say we take some sort of vector in my vector space, and suppose w and w prime in V both satisfy v plus w equals 0, and it also satisfies v plus w prime is equal to 0. Okay, so w and w prime are additive inverses. Well, then what can we say from there? Well, then we know that w, which is the same thing as w plus 0, is the same thing as w plus, and now look right here, we can rewrite 0 as v plus w prime. Okay, so that's for a substitution. Then we can use our associative property to regroup. So we have v plus w prime. And we can use the commutative property to have v plus w prime. But v plus w is 0, so we have 0 plus w prime, and that is just equal to w prime. So w is equal to w prime. So the additive inverse is unique. Okay, so this is kind of like the previous result, we can talk about the zero element, and like in this result here, what it says is when we have an element v, we can talk about the unique inverse, and because of that, we usually write minus v to mean the unique inverse of v. Okay, so i.e., what we have is v plus minus v is equal to 0. So minus v is saying that it's the inverse of v. Now, normally we don't write plus negative, all right? Normally we would write something like v minus w. What this is short for is v plus minus w. Okay, so this really you should read as take v and add the additive inverse of w. Okay, so that's what that means. So I'm going to pause. Maybe I'll do one more, and then I'll pause briefly, and maybe I'll just get you started, and then we'll come back after a short break here. So here's another theorem which says for any vector v, 0 times v is equal to 0. Okay, and before I take a little break, I just really want to highlight that 0 is being used in two different ways here. The 0 on the left-hand side means the scalar, 0. So this is coming inside of your field f. Your field f has a 0, so it's saying take that 0 element and you multiply it by your vector v. And on the right-hand side, you're getting the 0 vector of your vector space v. So the theorem is saying that if I take any vector and if I multiply it by the scalar 0, I get the 0 vector. Okay, so 0 is being used in two different ways, and it's something you should pay attention to in this course, is how is 0 being used. So I started the proof, and we'll finish off the proof after we take a little break, and we'll come to the part 4 of today's lecture.